So in this video, we're going to talk about 3 different techniques implemented in hardware that can help the compiler, the VLIW compiler, find more instruction level parallelism. And more specifically, we're going to allow the compiler to actually generate some speculation, to create some speculative execution. So the hardware support is going to help us in many respects. So we already know from when we played that we were compilers that one trick you often apply is that you would like to move loads up as high as possible and store down as far as possible. The problem is that there is a limit to how far you can move those instructions. Normally you cannot move instructions outside of the basic block, and there is also some load store, this ambiguity situations where you cannot tell if the load and store are to the same address, that creates problems, uncertainty about how far you can move the instructions. So that's one big problem for VLIW compiler designers, where you really need to find lots of instruction level parallelism. Another problem is that the basic blocks are too small. As we've seen before, unrolling helps a lot, but unrolling is also costly because you get such enormous code expansion if you have to do unrolling of every single little loop you have in your application. So we need techniques that allows larger moves, further moves of loads and stores and other instructions, and we also need to increase the size of the basic block. We have to do both these things to find enough instruction level parallelism. So we need to somehow allow loads to move above stores. And one way to do that is to have a way where we can make sure that the load and store are not the same address. We have to have a way for loads to move above branches. And one thing we have to look into, we have to guarantee that we're not going to get any false exceptions if we allow that to happen. And we have to have a way of sort of removing the branches or the effects of the branches. If we can remove some of the branches, that means that effectively the basic block is going to look like it's much larger to the compiler. And here we're going to look into a technique called predicate execution. So let's start with techniques, hardware support that could allow a compiler to safely move a load above a branch. So once more, the problem is you don't want to do this, is that this load down here may cause an exception. And that exception may not, and it could be an error exception. Crash and burn if we execute this instruction. But fortunately, this instruction is never executed because our hero, the branch, is sitting just above it and makes sure that we only execute this instruction when it's safe to do so. But what we would like to do here is to pull this load instruction high up in the execution to get more instruction level parallelism. And we want to do it in a safe way. So the kind of support that you get from the hardware implementers as well as from the instruction set of some of these VLIW implementations is to introduce a new kind of load. This load is called a speculative load. So what we do when this code is executed up here, which is above the branch, is to put the value identified by the R2 plus constant 100, that memory location, we move that into R1. Okay, and let's say that this is a 64-bit register. Doing that, we move it into R1, but then we have added a 65th bit, which is called the poison bit. And if this memory access caused an exception, TLB fault or whatever, then we're going to set the poison bit so that 65th bit of this register is now going to contain a 1, but life goes on. We just continue executing. We take this branch and we branch whatever we normally branch when we execute that branch. At the place in the code where we before had the load instruction that we now have moved up, we execute yet another load instruction. This is called load check. And all this instruction will do is to check to see if the 65th bit, the poison bit, if that one is set. If that bit is set, This is the point in time where we take the exception and not where the load actually happened. So that means that the exception will still happen in the right place. Yes, we will sometimes execute twice the amount of instructions. We will do the load speculative up here, load check down here. But this is a VLIW implementation with lots of parallel execution units. So having to execute one extra instruction now and then is the least of our problems. There's a very cheap price to pay for the ability to actually move loads past branches. So the speculative load instruction and the load check in combination makes that possible. The other problem we like to solve is to be able to move a load above a store, and even if we, from static analysis, cannot guarantee that this load and that store is not to the same memory location, because if it was to the same memory location, moving that load up here would violate the execution. Once more, we're going to add a little bit of hardware support to make such a move safe, even though we cannot guarantee that this load and this store is not to the same very same memory location. So we move the load up here. Once more, we have a new kind of instruction. This is called an advanced load. So whenever we would like to execute a load that's moved past a branch that we cannot guarantee is not to the same address, we do this advanced load instead. And the advanced load here will load the value into the register. At the same time, it's going to create an entry in a new hardware structure called the advanced load address table, ALAT. And we're going to put a tuple in that table containing the address we loaded from, as well as the register number. So ALAT is described down here. Advanced load address table is an associative data structure storing these tuples. So this is like a fully associative or highly associative cache where we store this tuple. Later on, when we perform a store operation, actually every time we perform a store operation, we're going to do a lookup in this ALAT. And more specifically, we're going to see if the address we're storing to has an entry in the ALAT. If it does, we're going to remove that entry from the ALAT. Now we come down and we do the other half of the load operation. This is called a load check, where we just make sure that nothing bad has happened. Load check R1. And here we go into the ALAT and we make sure that this entry containing R1 is still in the ALAT. If it's not in the ALAT, then we have to redo the load at this point. So maybe we take a software trap and we fix it right here. Or maybe we add some extra hardware support to fix it right here. But we have detected this probably rare event that this load and store is to the same address. And we make sure that we handle that in the right case, possibly by taking a software trap. So these are the two techniques that allow us to move loads and stores further distances in a sort of speculative way. And the last piece that we needed to give the VLIW compiler people was the ability to create larger basic blocks. Before doing that, we have a couple of questions. So what feature in this VLIW support allows a load to be moved up past a branch? Speculative load, advanced load, or branch prediction? Correct answer is speculative load. What feature is used to allow loads to be moved past stores even though they may be to the same address? And that's what's called the advanced load, that's hiding behind this pink box right here. So now we're going to try to come up with techniques that effectively makes the basic blocks larger. And why do we want to do this? Well, once more, basic blocks gives a larger makes more freedom for the compiler to pick and choose which instructions to execute in which order, and that could greatly improve the effectiveness of finding instruction level parallelism. The technique we're going to use is actually something very similar to what we've looked at before. We're going to look at something called conditional instructions. And one example of conditional instruction we talked about before when we talked about how to implement synchronization. So here we had an instruction called compare and swap, which said swap the contents of register 2 and 3, but only do that if register the contents of register 1 is equal to the contents of register 3. So it was sort of an instruction where we wanted it to have some side effect, but only under certain conditions. There is a different type of instruction as well, which is conditional move. So this conditional move register the contents of register 2 to 1, but only do that if register 0 is equal to 0. So this is kind of instructions you would find in some ISAs. We're going to sort of make use of these conditional instructions, but we're going to do it in a much generalized way, and we're going to make all instruction give them the ability to be conditional instructions. And we're going to use something called predicate execution. And in order for us to implement the predicate execution, we're going to introduce a whole set of new instructions. And these instructions are a whole set of new registers. And these registers are very small registers. Actually, each register only contains a single bit, a 1-bit register. And we're going to have a large number of these predicate registers, and we're going to combine them with normal instructions. So I'm going to explain what's going on with a simple example. So if you have a code like this, where you have some if statement, you do little stuff, and then you have else statement, and you do little stuff, and then you end. If you compile this kind of code down to normal, some kind of instruction set, then you may set some, start by executing some condition saying that if R1 is larger than R2, then put a 1 in R3, otherwise put a 0 there. So we just put a conditional outcome here of comparing R1 with R2. Then we have the branch instruction, branch if not 0, R3, and we jump to the else if that's the case. We execute those two instructions. Otherwise, if it's the then case, we just go on and execute these two instructions, and then we branch to the end. So we jump over the else case. So here, just counting the number of instructions, we have 5 instructions executed, and they're going to be 5 instructions executed during the end, the then path. So 1, 2, 3, 4, 5, branching down here. And if it's the else path, we're going to execute 1, 2, and then we do the branch here, and then 3, 4. So we have, worst case, we have 5 instructions to execute, and we have 2 branches in this course. One is a conditional branch, the other one is a non-conditional branch. If we instead use predicate registers to execute the same code, this is what it will look like. So we have one instruction that sets predicate register values, and that in one instruction would look something like this. If R1 is larger than R2, then set some value in one predicate register to 1 and in its corresponding predicate register to 0, else vice versa. So you can compare this with this conditional register. We sort of set a conditional value in one register. So it's very similar to what's being done here. Depending if R1 is larger than R2 or not, we set the value, single bit value in 2 different registers. Here we just set a value in one register. So implementation point of view, very similar. Then we guard each of the following instructions with one predicate register. So this is P6 : that means only let this instruction have side effects if P6 is equal to 1. Same thing with the next one. And then the following instructions that says let only this instruction have a side effect if P7 is equal to 1. Okay, so it's either these two instructions or the following two instructions will have some side effect. Then what we do in this execution is we just execute everything in a straight line. So set the conditional, the predicate registers in one instruction, and then we execute all instructions, even though we only need to execute two of these two following instructions. Because, once more, this is a VLIW implementation, and the least of our worry is to have to execute a couple of instructions too many. What is much more important is that we now remove the effect of this branch. We're going to come executing from above here. We're always going to execute these 5 instructions and always going to continue. So in some sense, from the compiler's point of view, we have taken away the nastiness of chopping up the execution into small basic blocks and make this basic block part of the previous basic block as well as the following basic block. And that will allow us to for the compiler to generate much more efficient code. So comparing hardware to software speculation, it's clear that hardware speculation is potentially could have higher performance because we dynamically can do the disambiguation of memory addresses. We dynamically can do branch prediction, which is probably much better. We can learn as we go rather than to trust the compiler. And we can do hardware speculation to maintain the precise exception. We don't have to execute all these extra instructions with a speculative load and the check load and so on. So it's better, but the main disadvantage is it is very complex to implement that out of order checks and reordering. And if we instead could help the compiler do a good job in finding instruction level parallelism, that potentially could be a much better solution. So in the next video that's going to be released in the next module, I will discuss one of these implementations, IA64 or the Itanium processor. Another very recent implementation of VLIW is the Transmeta processor from early 2000, which was a design that actually competed head-to-head with Intel for many years of being the most energy-efficient implementation, and that was also a VLIW implementation. We're not going to cover that in this course.